Welcome back to my Commodore 64 Retro Games video series. I noticed a comment from the Games That Weren't website about an Alleykat self-playing demo version. Alleykat, of course, was published by Hewson. Now, this demo version seems to have the self-playing capability where it goes through some attract mode and then it goes into the levels to demonstrate the game's functionality. Maybe it was something for the magazines or for shops to display. Anyway, the Games That Weren't website was asking if it was possible to make it playable. So let's have a look to see what they have and then see if we can alter the code to make it playable. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are all always very much appreciated. So the first thing that you notice is that this tape loader looks a little bit familiar. I've seen this kind of tape loader from Andrew Braybrook before. I'm whizzing through here in ICU C64. I've engaged the turbo mode, or the warp mode rather, and it loads a bit quicker. We'll just get these windows in sensible positions. There we go. I don't see anything especially intriguing in the initial data that's being loaded. It's a nice little loading thing for a self-playing demo. That's true, but it's kind of like reusing some of the earlier, I think, loading code. Anyway, so this is the tape turbo loading code there in the monitor. Just having a quick little look through to see what it does. There's various different bits of loading code and border color setting and things like that. Just having a little scroll through to see if I can find where the entry point might be. That might be the final jump at CFD0. Let's have a look. And let's see what we get. Well, it's just about to jump into CFD0. And CFD0 is, basically it's some code which was copied from just after. There we go. So it's restoring a state into the processor port, which is mapping or unmapping the kernel and basic ROMs. Looks like it's doing a checksum check and doing a branch on equal, and then it does a SEI, CLD, and then a jump indirected with the reset vector in memory. Okay, so that looks like a really good position to start saving this out. The goal here is to make the game playable and then save out a nice compressed version of the game as well, so that it can be easily run from a program file rather than loading it from tape, for example. And the Games That Weren't website has the tape version already. I just want to have a nicely compressed PRG, which is easier to load. Okay, so we'll just save all of that memory, and yes, the bank RAM option is enabled, so it's saving out all of the RAM, basically between 200 and FFFF. This indirected jump through the reset vector at 8000 seems to go into the game startup code, which stops interrupts, clears the decimal flag again, grabs all of the stack, and then sets the processor port. So this is the attract mode in the game. We have some cool memory stuff going on here. I'm also, well, because it's self-playing, I'm looking for bits of memory which have sequential read patterns, because I'm looking for, hopefully, something which is going to be really easy, and that's where there's just a whole bunch of recorded joystick presses in memory, and it's just reading those and then playing those back through the regular joystick code routines. Unfortunately, in the memory view at the moment, I don't see a lot of sequential reads. And if we go through a few more iterations in this, I can see, okay, it's going back through the attract mode. There seem to be, yes, okay, just seeing where that code was, and yeah, the attract mode seems to be looping around again. And it's showing all of the enemies and things. I don't see sequential reads. This means that it's going to be harder to figure out what's going on. And look, it's a different level, isn't it? And the gameplay is different as well. Fantastic. Okay, this means that it's going to be really very difficult to actually try and make this a playable thing. Oh, look, yeah. Different level again and different gameplay. Okay. Okie dokie. So I've noticed actually here I can press the function keys and I can choose between 1 and 2 player mode, 2 or 1 and 2 joysticks. I can decrease and increase the volume for the music and also change it between color and black and white as well. This is by pressing the function keys F1 to F8. So there are some function key reading routines that are still being called in the title screen. Okay. But there don't seem to be any routines which read the joystick. So what can we do? Well, we can try and look for some usages of the bit instruction, bit absolute, basically to see if we can find any code which is trying to extract joystick bits. There seem to be rather a lot of occurrences of the 2C byte, which might indicate a bit instruction, but also it might indicate other data in memory which is not related to the bit absolute opcode. So I don't think that these memory addresses are related to reading recorded joystick reads either. They aren't sequentially increasing or anything like that. Let's see if we can find anything which stores into the SID, and then let's see if we can disable the music to see if we can make the memory view easier to view. So we're going to temporarily disable the music routine by locating the music routine. There we go, there's the JSR to the music routine. Basically looking for stores into the sound chip registers and then back tracing or hopping out of that subroutine until we find the JSR to what looks like the music routine. We just comment it out with 3 no-ops. Yeah. So I'll just take a backup of what's there if I want to restore it later on before commenting it out with some no-ops. But we'll just put 3 EAs there, which is 3 no-op single byte instructions. That gets rid of the JSR. This reduces somewhat the clutter in the debug memory view, event memory view window, anyway, in ICU64, to see if we can more easily spot some sequential reads, because now the music routine is not doing stuff, and the music routine is usually quite a culprit for accessing quite a lot of memory. Again, cycling through the game in warp mode, I don't see anything which jumps out at me in terms of memory patterns for sequential joystick reads through the memory, which is a little bit upsetting and depressing. It means that the code is going to be a lot more involved. So there's no, I'm pretty sure now I can safely say that there's no pre-recorded joystick data in memory. So we need to find other joystick code. So what we can try and do now is that we can see if there's any kind of like code which looks at the joystick A or B memory locations. That's DC000 and DC001. We'll hunt through the memory. Let's just double check that we're in the bank for RAM rather than including ROM or IO. Oh dear. There's no bit going on specifically for the joystick port 1 or port 2 locations. However, maybe there's enough. Now look at that. These are the memory locations that access maybe DC00 and DC01, which are the 2 joystick port registers, plus the keyboard stuff as well, but joystick port registers. these memory addresses seem to have some commonality. In other words, they're quite close to each other, and there seems to be some overlap there. So let's have a look at these routines. Look at that. This is storing FF into DC00, then loading DC01 and doing a bit with AD57 branch on equal bit AD58. Haha! This looks like it might be a joystick reading routine because it's doing the joystick register setup and then doing a read. So it looks like, tracing back through the routine, it looks like that it's actually not kernel. It's not basic code. I just had a quick look at the basic disassembly, the basic interpreter ROM, and it's actually not there. It's not, just double checking that it wasn't actually in the basic code. So this does look like it's joystick reading, maybe. This looks like the entry point for the routine at AD19. Anyway, looking at the code, I think that's going down a little bit too far. Just scanning through to see if there's anything else interesting after that. But I don't think there's anything else interesting after that. So, but there are some there's some keyboard matrix setup going on here. So there's a store to DC00, you see, and then it loads from DC01. So that kind of like sets up, I think, if I remember correctly, the keyboard sense lines, and then it's reading the scan result from the keyboard matrix. So yeah, that's the function key reading routine. Just trying to refamiliarize myself with the memory addresses that I'm seeing here. So this routine here seems to be storing into $20 as a result, perhaps, of the keyboard matrix values. Yeah, okay. So if you want to read the keyboard matrix on the Commodore 64, you have to scan. I forget if it's each row and then you get a different column around, or if it's each column and then you get a different row for the intersection of which keys are in the matrix. But basically you have to scan across or down the keyboard, and then you detect which keys in that scanning across or down are actually pressed down. So I think that routine was the keyboard scanning routine for the attract mode for the function keys being held down. Let's investigate further. So we'll let the game play through its level, then we press, there we go, aha. Okay, so it's got back to the attract mode and it's breaking into that code there. Yeah, and then that is definitely the function key read for the title screen. I pressed the function key and then it hit that breakpoint. So that's good. That's interesting to note. There's that memory address there. It's 6E2F as well. There's AD22, AD25. Just updating the notes for where the function key read routine is stored, because we'll need to know this later on so that we don't try and duplicate the effort that we've done already into identifying where these routines sit in memory. So AD22, this routine here. Now, if we trace back through AD22, we've got these bits going on here. AD3D, yeah. So if the relevant joystick bit patterns are stored in those absolute memory addresses, which is quite a sensible way of doing it, then this routine seems to be doing a bit test against directions which are held down in the joystick. It's not the volume test, is it? No. Yeah, I'm pretty sure that this is the joystick code. Let's investigate further. Well, with a breakpoint in that routine during the game, self-playing game anyway, it's not hitting that breakpoint in that routine, so I'm pretty sure that that code is not calling what looks like joystick decoding. If I scroll back up again here, you can see that that's where the breakpoints were, and those breakpoints didn't actually get hit. Looking at this routine, it looks like it's definitely included but not called, but well, at least it's not called by the self-playing demo anyway. There might be a routine nearby in memory. If the routine is there in memory but not being called, but so maybe there's something else which is decompressing or reading or creating joystick inputs at this stage. I think it's using probably either some very rudimentary kind of like logic or AI, or maybe some random input or pseudo-random input. There's this routine here, which is just in memory previous to the proposed joystick bit decoding routine. Doesn't that look interesting? It's actually updating memory address 17 in 0 page, $17, which in hex, right? And it's also updating 16, which is adjacent to it. So maybe that's incrementing and decrementing X and Y movement, right? In this proposed joystick bits decoding routine. So yeah, 17 and 16 and 18. 18 is doing it with it's got a flag with hex 10, which is the fire button, right? If I remember my joystick bits, then up, down, left, and right are the first 4 bits. The order might not be correct, and then the next bit along, the 5th bit, in other words, $10 in hex, is fire. So I think this is almost certainly a joystick bits decoding routine, but it's not getting called. Interesting. So I have an idea. Let's look for any access to 16, 17, or 18 in terms of memory. Aha. Okay, so I'm looking for access in 16, 17, or 18 in memory because that's where the joystick routine was decoding the joystick bits to. In other words, direction of movement, and also the flag to indicate the fire button being held down. However, the routine wasn't getting called. However, those memory locations, as we can see, were being accessed by the game. So even though the joystick bits decoding routine is not being called, the results of that, those 0 page locations are being reused. Now, D41B is the waveform output register, which is commonly used by it's a SID chip register, a sound chip register, but it's commonly used for generating pseudo-random numbers. It's a pseudo-random number source, if you like, especially if your voice 3 waveform is the noise waveform, for example. Then it generates relatively good random, pseudo-random numbers. So basically this code is doing something with a pseudo-random number source and then storing some results into 16 and 17 and 18. So it looks like the gameplay and the self-playing demo, at the least, is using the pseudo-random number generation source from the SID chip plus some other calculations. Maybe it's indexing into a different table or something like that. And then, or just indexing into some memory which happens to generate good gameplay results. And then it is updating those joystick bit registers. So what we could do, right, is that we could, instead of using the routine that sources data from the pseudo-random number generator and then stores into 16, 17, and 18, I think we could not call that routine, and we could call the joystick read routine instead. Let's see if we can find... I noticed that it's also updating EE and ED as well in terms of zero-page memory locations. So there's some updates of the EE zero-page memory location and ED as well. Maybe EE and ED are used to flag something else being pressed in game, perhaps. This needs a little bit more investigation. Look, I can see that there's another load from the SID chip, the sound chip pseudo-random number generator source, the third voice waveform source, basically. D41B, load A D41B, just below that breakpoint there. So these routines, there's at least two different routines which have very similar structure. Okay. Let's scroll up a bit, see if we can see if there's any originating routine. Oh, there's another one. There's another pseudo-random number generator source routine. And, okay, it seems to be... That's weird. Is it going around in a cycle and calling different routines, kind of like in a cycle to generate different pseudo-randomized movement for the player, perhaps? That's what it looks like, because don't forget it's storing information into the zero-page memory locations at 16, 17, and 18, which indicate decoded joystick input. But it's decoded joystick input that comes from a pseudo-random routine. Okay. Let's see if we can hunt through memory for other places in the code which do a similar load with the pseudo-random number generator register inside the sound chip. There's quite a lot of them. Again, that's a little bit annoying and depressing because technically they would need to get investigated. I think we look for here's the start of the routine, was it? So let's hunt for places in code which call that routine, which seem to be generating randomized joystick outputs. Okay. So that's D87, which is the start. It looks like it's the start of the routine anyway, right? Because it does a JSR and then a load Y. That looks like, okay, there's only two places in memory where it calls this routine. It's C9B and then D4E. Okay. Player 1 and player 2, perhaps? And that's why it's only calling it twice? Let's just double check. C9B and D4E. Let's typo. Let's see how often these are called. So it's always doing one frame. Oh, okay. One frame update every time it hits this breakpoint. Okay. So I have an idea. Let's override that JSR to D87 and replace it with what we think is the joystick bits decoding routine, right? And then let's see what happens. So we'll replace the call to the random number based routine, and we'll change it to the actual real hardware register for the joystick bits decoding routine. Okay. So we can do that just by changing the address of the subroutine at the correct memory location for the JSR, the jump on subroutine instruction. Okay, so we'll change that to 21AD, which is AD21. Don't forget that it's a little endian processor, so that it's low byte, high byte order in memory. Huh. Well, that doesn't seem to help. Why is that? It's not responding to joystick movement. Did I put the wrong memory address in there? I did. It's meant to be AD19, not AD21. If you're watching, did you spot that mistake before I noticed it? Anyway, so there we go. Right, now it's triggering the joystick bits decoding routine. There we go. Now, oh look. Well, hey! Okay, so it's playable. So this is great. So that's the kind of like a poke, if you like, for that you would have to add to the self-playing demo to make it playable by the player. Let's... Oh, whoops, I've just corrupted the JSR instruction, which is 20. There we go. Let's put it back again, but then we'll... Okay, now that's the correct memory address. So that's the correct poke. So there are two pokes to replace those two different calls. Perhaps it's for player 1, player 2. Okay, I don't think I needed to change both, but just for completeness sake, change both. Now we need to loop around again now and wait for the attract mode to get back to the game. Okay, that was quicker than expected. There we go. It's playable with those simple pokes to replace the pseudo-random player input to be the decoded joystick bits player input routine. So it's lucky that it was sitting in memory. It allowed us to narrow down the code and actually find the pseudo-random player input routine by looking for the specific 0-page memory locations, 16, 17, 18, wasn't it, in memory that held the decoded joystick bits. So now what I think that we should do is that we should look through the code and try and make the attract mode go into the game when we press fire, because at the moment, if I press fire on the joystick, you see I'm pressing fire in the emulator there, the attract mode completely ignores the fire button and doesn't go into the game at all. So I think we need to trace through now into the attract mode to see if we can get the attract mode to exit into the game when I press fire, because I don't want to have to wait for the attract mode to cycle around again before I can actually play the game. So breaking into the execution here by opening the monitor window, I can start the trace through the title screen code, the attract mode stuff. This might take quite some time. This is going to be quite laborious tracing through the code. That's an interrupt. I can see because it's updating FFFE and FFFF. There's a whole bunch of TXA, PHAs, TYA, PHA instructions, and then there's an RTI and everything else. Oh yeah, this is the commented out interrupt routine, which was calling the music player. There we go. So, what does 1DF8, what does that routine do? We'll have a little look. Okay, seems to be updating something in those memory locations. Doesn't seem to be doing much. Might be clearing stuff, copying perhaps. Maybe it's the color cycle table, maybe. Right, okay. Yes, okay, so 2A is like the vsync completed flag, I think. Looking at this code, it kind of like makes sense that you would... There are two ways. You can either check for a raster position on the screen as the raster beam goes down the screen, or you can just check for a flag which has been updated by a raster interrupt, and this game seems to be doing the latter. So we have some code here which I don't know what it's doing. We'll step through, see what it does. Okay. So it seems to be going around in a relatively small, tight loop with some subroutines. It's doing what looks like just table updates and stuff like that, which, because it's on the attract mode screen, is not really a great surprise at this stage. Yeah, I mean the attract mode, which is basically a whole bunch of different screens and the high score table and stuff like that, and also an enemy encyclopedia, if you like, has animating color bars and things like that. So this is not unexpected, right? This just needs more tracing through. I think I might speed up the video here, and once I find something interesting, then I'll move it back to normal speed. So in this sped up section, I found something which looked like a frame counter which was being updated during the attract mode. And this frame counter was used to trigger various different screen transitions in the attract mode. Eventually, the attract mode would then get back to launching the game, which is where we are now. So I'm looking for some code or some free memory space so that I can actually add some code to check the joystick routine, or to call the joystick bits decoding routine while the attract mode is running, and then quickly jump to ACA, which is where the attract mode sequence gets to when it wants to start the game. ACA seems to be a general purpose entry point for starting the game code because it does a whole bunch of stack reclamation and stopping all of the interrupts and everything. It seems to be a very hard stop at that point. It seems to be a very good place to just jump into the main game code there from the attract mode screen. So I think 400 in the memory map looks like it's free. Look, 400 is the Commodore 64 basic V2 default screen memory message that is still available as the game is running. So I'm pretty sure that that's free memory. What I'm doing is that I'm going to insert some code into here at 400. So I'm just basically jumping out from the attract mode common routine. So this attract mode common routine is incrementing the frame counter pointer, and it's also doing a vsync or a vblank wait as well. But I'm circumventing that routine by hopping out and then going into this new code. So this new code will do a JSR to AD19, and AD19 is the joystick bits decoding routine, which also detects for the fire button and also decodes the up, down, left and right, all the player movement stuff, right? So that's that routine there. I want to look for the fire button coming into 0 page memory location 18. I want to, if it's branch on equal, then it's 0. So I want to branch on equal to over the following jump. So the following jump is going to be jumping to ACA. Whoops, the syntax is wrong. I need to put a dollar in front of ACA. There we go. And then the memory location after that is 40A, which is where the branch on equal gets to. And then the branch on equal will continue to re-implement the code in that common inside the common attract mode vsync wait and the frame counter update routine, right? So what was there previously? I don't quite remember. I've just destroyed it with that jump to 400 in hex. Okay, let's find out what was there previously. Just opening a new instance of the game, disassembling 1F97. Oh yes, that's right. Load A with 2A and a branch on equal back to 1F97. So 2A is the vsync event register 0-page memory locations. I call them registers because they are like extended register set in the 6502, 6510, because they're quicker to access than the absolute memory addresses. So there we go. Do the vsync check and then jump back into the rest of the routine at 1F9B. And the rest of the routine at 1F9B does the frame counter increment in those two 0-page memory locations. Okay. Just double checking the code. Looks like it's okay. Let's check to see the code gets the new code, my circumvention code. I can see the code actually in the graphics debug map there in the top of the screen, just above the Commodore 64 basic v2 message. Oh, okay, it's jumping straight into the game at ACA, even though I did not press fire. Why is that? Okay, it should be a branch on not equal to 40A, not a branch on equal. Obviously, I've got the flag the wrong way around. So let's note that back down into my debugging notes text file. As usual, I will be committing the debugging notes text file and everything else into source control, so you can also see the steps that I went through when I was debugging this. There we go. Now pressing fire takes me into the game. Of course, I loaded the game that did not have the modifications for the playable joystick bits decoding routine there. So there we go. Now I've made it playable by including the joystick bits routine. There we go. So now I can press fire in the attract mode and then I can go straight into the game and then play it. Fantastic. So the attract mode, when you enter the game, does display a choose level. Ooh, that's crashed. Why is that crashed? Oh, okay. The game code, when it goes into the game, seems to have corrupted the memory at 400 in hex, which is where I put that replacement code. Okay, so I need to look for a memory location which is really free and available throughout the attract mode and also the playable game. So let's load all that code again from the Alleykat code just after the load had finished, right? So there we go. That's the code. Let's look for some memory which is not being altered by going into the game and then coming back out to the attract mode. So, oh dear, look. This memory location there, well, that looks like it's available, doesn't it? So that's 200. That's just after the stack. Oh no, it's not. It's before the stack. Yeah, okay, so 140 in hex, which is near the beginning of the stack, but not quite in the middle, but in the beginning. Yeah, 140 in hex is free, but it's too low. If I want to compress this, then the decompression code actually runs in the lower part of the stack, so I can't use that. So let's look elsewhere for what looks like a nice empty block of memory. Well, looking at this, that's that memory location there. That's going to be available, perhaps. Let's just have a look at this in bitmap mode. Maybe this gives us more insight about where the blank empty memory is. Yeah, okay. So yeah, I think that memory there is graphical memory. It looks like it might be a character set or something. It's certainly not screen memory. It might be sprites, I suppose. Anyway, cycling through the intro attract sequence, going into the game, out of the game. I'm in warp mode here, by the way, so that's why it's going by so very, very fast. Going through that cycle seems to indicate that that memory is still staying empty. Okay, it's filled with zeros, which is even better and even easier to spot. So, is this memory going to be used at all during the attract mode? Well, we can find that out by using the monitor with a watch point. So we'll do that. We'll look between F700 and F780. We don't need that many bytes for the override code, which inserts the joystick bits decode reading routine into the attract mode sequence code. So yeah, that looks like it's not triggering any watch point for the memory being read or executed or written to. So let's load the Alleykat code again, and let's put in all of the pokes again that we needed before to get the playable code in there, and also the code which calls the joystick bits decoding routine in the attract mode sequence. And let's put all of that stuff in there again. Need to make sure that we assemble the code in the right place. So we will be using now F700, not 400 in hex. So we'll just be typing this in. No, not 400, F700. There we go. We're typing this code in again. Load accumulator with 1.8 in hex, which is the joystick fire. We don't want F703, right? We want F708 there. We'll carry on with the rest of the code. So we want the jump to ACA with a dollar in front of it, so we don't get the syntax error. Then we look for the vsync flag, and then we loop around until we get the vsync flag or the vblank flag from the interrupt, right? So we need to loop around now, back again, and then we jump back to the real game code once we have finished circumventing the attract mode code. Need to remember to save the code. I forgot to save it last time when I ran it, and that wasn't very good. Let's save it as a proper file name. So self-playing one. No, it's playing, right? So we'll play version 1. Let's save that code. Save the work that we've done. Now we can run the entry point start, which is what the tape loader would have done. Okay, so let's press fire. We've still got the code there in the memory. There we go. Press fire. This is automatically choosing the level or something that you need to get to the game. It would be nice to make that screen joystick capable, wouldn't it? But anyway, once pressing fire in the attract mode and it picks the level to go to, then we can play the level that we want to play. Or rather, we're playing a level that the game wants us to play because it chose this level. We didn't have any say in the matter. So there we go. Now we have a playable game from this demo that the Games That Weren't website kind of like found. It would be interesting to know why this self-playing demo was created. Was it for a magazine review copy? Was it for self-playing demonstration in the shops? It would be really interesting to find out from the original author, of course, Andrew Braybrook. I wonder if he'll see the Games That Weren't website and provide a hint about what this is all about. So I really enjoyed doing this for the Games That Weren't website. It's quite a nice little challenge to find the relevant code for a self-playing demo which doesn't rely on recorded joystick inputs in memory. So this self-playing demo was a little bit unusual. It relied on pseudo-random number generation with the SID chip. So what we can do now is that now we have that saved working version of all of the RAM. I can use my LZMPI compression utility to compress it, and we can see that it actually compresses it really well and produces a nice small single PRG file. And there we go. It decompresses. I had warp mode turned on, so it was a lot faster. But yeah, basically it flashes the border, decompresses, goes into the attract mode. The attract mode, press fire, and then I can start playing the level that the game has chosen for me. And there we go. I will also commit that Alleykat demo play.prg file into my debugging details GitHub repository, and I'll send the copy as well to the Games That Weren't website. And I think we'll leave this video there. Thank you very much for watching these Commodore 64 coding videos and games, retro games, memories videos. If you like this kind of stuff, then please do consider liking or subscribing to this channel, and I really hope to catch you around next time. Have a great day, evening or night, wherever you are.